Thank you.
So the next speaker is the Wen Fao.
Yes, can you see my screen?
Yeah, I can see.
Great.
Yeah, thanks. Please, yeah.
Yeah, sure. Hello, everyone. I'm Wen Hao from Carnegie Mellon. Today, I'm going to briefly talk about our work on safe learning for online nonlinear control. This is a joint work with my colleague, Dr. Wenson from Cornell and Dr. Ashish Kapoor from Microsoft. As we know, safety in terms of collision avoidance is critical in deploying the autonomous systems to the real world. And in order to derive the safety guarantee, we often have to rely on perfect information, such as system dynamics for the robots, in order for them to design controllers that keep them stay inside a safety set. However, in the real world, if we do not have this perfectly modeled system, then we have to use learning to model it. For example, consider the model-based reinforcement learning, where the robots keep interacting with the environment and collecting data to approximate to its ground truth dynamics, and then for the task performance optimization. Even if the task could, for example, teach the robots how to run on the rough terrain, it could still suffer from unexpected failures because of this imperfect model and the resulting lack of safety consideration. To that end, we want to bridge the control method and also the machine learning so that we can intuitively have the robots to working along the boundary and safely explore the unknown system dynamics. So in our paper, our contribution is a sample efficient safe learning algorithm for control. So first of all, our algorithm could guarantee safety when exploring the environment despite the imperfectly modeled dynamics. And second, instead of just letting the robots stay still and doing nothing, we wanted the robots to ensure efficient exploration to learn the system dynamics. And lastly, besides this exploration and safety guarantee, we also want the robots to achieve good performance in terms of maximizing the total rewards, because we don't want the robots to densely exploring everywhere just for learning the system. So let's look at our problem formulation and setup here. We consider the discrete time control affine system consisting of nominal dynamics known to the robots and an unknown dynamics that need to be learned by the robots. So specifically, we assume these unknown dynamics could be represented by a dot product between an unknown linear mapping, W star here, and a known feature mapping. So basically, with all the training data, the learning of the dynamics boils down to the approximation of this unknown linear mapping W. If we know the system dynamics, then the classical control task is just trying to find an optimal policy that minimizing the task-related cumulative cost function subject to some safety constraints, for example, represented using the control barrier function. However, with this system unknown, we have to change it to a learning-enabled objective function. So considering the learning process of T episodes, our objective is to minimize the regret, reflecting the performance deviation of control policies from our learner online from the another control policy that is optimal if assuming we have access to the ground truth dynamics. And likewise, we want to maintain safety at all times, even with this unknown dynamics learned online. So in the paper, we show that we're able to derive algorithms that enjoys the sublinear regret bound in terms of number of episodes. So here, let's look at some simple examples of our running our algorithms. Initially, we consider a invented pendulum that with a nominal model, it is very hard for the robots to stabilize the pendulum and not cross this blue stick as the safety constraints. And starting with a bunch of training data, we are able to utilize in supervised learning, such as linear regression, to find a good representation of the model represented by the W here. And with that, we are able to utilize in the off-the-shelf optimal planner that first of all sample a candidate dynamics from your current knowledge, and then to feed into a control framework using control barrier function so that we could generate some optimism-based exploring actions that are safe with high probability. And by feeding this into the pendulum, we're able to see it will start collecting data and then start improving performance. And after closing the gap, we are able to keep running. And in between of, for example, iteration 30, the pendulum will be able to gradually improve its performance and not cross this blue stick as violating of the safety constraints. And in the end, the robots were able to successfully achieve the optimal configurations and most importantly, remain safe at all times. So in the paper, we have extended experimental results illustrating how this algorithm works and all this analysis and proofs. So to wrap up, we propose a sample efficient, safe learning framework for control that enjoying, first of all, the bounded regret guarantee and also ensure the approvable approximate safety guarantee. So the first work, including the experiment in the real world and also extending to more complicated safety constraints. With that, I'd like to conclude here. Thank you.
Thank you, Wenfao, for your very interesting talk. Yeah.